In this module, we will start the discussion of experimental methods allowing to determine the reaction order. Let us consider the reaction of two substances A and B. In general, we can expect that the rate law expression for this reaction is given by this expression. V equals K times the concentration of A in the power of Na times the concentration of B in the power of Nb. Here, Na and Nb are not yet known reaction orders of this reaction with respect to reactants A and B. How can we determine the order of the reaction with respect to A and B? First, the measurement of the rate under a single set of concentrations for A and B is not sufficient to measure Na and Nb because there is only one equation and three unknown quantities. The rate constant cannot be determined before the reaction orders are known. Therefore, the determination of reaction orders and of the rate constant will involve the measurement of the reaction rate under various concentration conditions. Now, we should ask ourselves what set of concentrations should be used to determine the reaction rate in order to conveniently determine the reaction orders. One answer to this question is known as the isolation method. The isolation method simplifies the determination of a rate law by performing the reaction with all but one reactant in large excess. In this approach, only the concentration of the non-excess reactant significantly varies during the reaction. For example, consider again the reaction between A and B shown before. Imagine performing this experiment in which the initial concentration of A is 1 mole per liter and the concentration of B is 0.01 mole per liter. When all of reactant B has been used, the concentration of A will have been reduced to 0.99 mole per liter, only a slight reduction from the initial concentration. This simple example demonstrates that the concentration of reactants present in excess will be essentially constant with time. This time independence of concentration of reactants present in excess simplifies the reaction rate expression because the reaction rate will depend only on the concentration of the reactant not present in excess. In our example reaction, when A is in excess, the rate law simplifies to V equals Kf times the concentration of B in the power of Nb. Here, Kf is the effective rate constant for a given fixed concentration of A. This quantity is taken to be time independent because K is constant in time and the concentration of A will change only slightly with time because A is in excess. In this limit, the reaction rate depends on the concentration of B exclusively, and the reaction order with respect to B is determined by measuring the reaction rate as the concentration of B is varied. If, instead, the concentration of B is in large excess and hence effectively constant, then the original rate law simplifies to V equals K prime F times the concentration of A in the power of Na. Here, K prime F is another effective rate constant corresponding to the given concentration of B. Note that the order of the reaction and the form of the effective rate constant change according to whether A or B is in excess. Related to the isolation method of determining reaction orders is the concept of pseudo-order reactions. If the excess of a reactant simplifies the rate law to a first-order form, we are dealing with a rate law of pseudo-first-order reaction and a first-order effective rate constant. Similarly, if the simplification results in a second-order form of the rate law, the reaction is called a pseudo-second-order reaction with a corresponding second-order effective rate constant. The key difference between true and pseudo-rate laws lies in the dependency of the effective rate constant on the concentration of the reactant in excess. In true rate laws, the rate constant is independent of the concentrations of all reactants. The concept of pseudo-rate laws is particularly relevant in reactions occurring in aqueous solutions. Water, being the solvent, is present in such a large excess that its concentration does not change in the course of a chemical reaction. Many reactions in aqueous solution reported as first or second order are in reality pseudo-first or pseudo-second order. By systematically isolating each reactant while maintaining others in excess, we can individually assess the rate's dependence on each reactant. This approach enables us to assemble the overrate rate law from pieces, understanding the contribution of each reactant to the reaction kinetics.